Can we send signals faster than light? This question strikes at the heart of modern physics and human imagination. If information could travel beyond light speed, we might communicate instantly across galaxies, reshaping our understanding of time and space itself. Yet, this idea doesn't just promise faster communication. It threatens the very structure of reality, challenging Einstein's relativity and the rule that cause must precede effect. The mystery of faster-than-light communication isn't just scientific, it's philosophical, daring us to ask whether the universe's speed limit is a boundary or a doorway. And if you want to uncover the full story, then watch this video till the end and subscribe to the channel. Let's begin. The reason light holds the title of the universe's ultimate speed limit lies deep within the laws of relativity. According to Einstein's theory, space and time are not separate entities, but parts of one unified fabric, space-time. When something moves through this fabric, it doesn't just move through space, it also moves through time. Light, traveling at roughly 299,792 kilometers per second, moves along the fastest possible path that space-time allows. Nothing with mass can ever reach this speed, because as an object accelerates, its mass effectively increases, demanding exponentially more energy to keep going. To hit light speed would require infinite energy, something no known force in the universe can provide. But this isn't simply a matter of mechanical limitation. It's about the way the universe fundamentally works. The speed of light acts as a cosmic speed constant, a cornerstone built into the structure of reality itself. It doesn't just limit how fast things can move, it defines how time and space behave for anything that does move. Clocks tick slower and lengths contract as an object approaches light speed, meaning time and distance themselves bend around this limit. In essence, the speed of light isn't merely fast, it's the speed of causality, the rate at which information and influence can ripple through the cosmos. To surpass it wouldn't just be to move faster, it would mean to defy the logic of cause and effect. This brings us naturally to what relativity actually says, because Einstein's theory isn't just imposing a speed cap for the sake of it, it's describing how the universe itself is structured. In relativity, space and time are interwoven into a single continuum called space-time, and the speed of light is the constant that links them. It's not just a number, it's the conversion factor that connects how far you move through space with how much you move through time. This means that when you approach light speed, you're not just moving faster, you're warping your experience of time and distance. If anything could move faster than light, it would distort this delicate structure in a way that breaks the very logic of the universe. Events that should happen in a sequence could suddenly reverse. A message could arrive before it was sent. A cause could follow its own effect. This isn't just theoretical confusion. It's a collapse of causality, the backbone of reason itself. The equations of relativity make it clear. Exceeding light speed means entering a regime where time and order lose their meaning, and reality becomes inconsistent. The universe, as far as we understand it, simply doesn't allow that kind of contradiction. When we talk about the speed limit of light, it's easy to imagine that physics forbids anything from moving faster than light. But the truth is subtler and much more fascinating. There's an important difference between something that merely appears to move faster than light and the transfer of actual information faster than light. This distinction lies at the heart of how relativity preserves causality, and it's one of the most misunderstood aspects of modern physics. In physics, information means any measurable, meaningful signal that can cause a change or communicate something from one place to another. It's not just about motion, it's about cause and effect. A signal, by definition, must carry energy or data that can influence another location. And this is where the light speed limit truly matters. While certain patterns, waves, or mathematical effects can appear to move faster than light, they do not carry new information, and therefore they do not break relativity. Imagine a row of dominoes stretching for miles. If you tip the first one, the motion of falling dominoes moves down the line at a certain speed. But if, instead, you were to flick each domino in perfect timing using a synchronized mechanism, the pattern of falling might seem instantaneous, as though the falling effect traveled faster than the real motion between dominoes. However, the synchronization was already set up before the motion began. No new signal was transmitted faster than light. The effect looked fast, but it wasn't truly conveying new information instantaneously. This distinction becomes even clearer when we talk about waves. In a wave, there are different types of velocities, phase velocity and group velocity, which we'll explore more deeply in the next segment. The key idea here is that the peaks of a wave, the phase, can appear to move faster than light, but the actual energy or message, the group velocity, does not. The universe, it turns out, allows appearances that seem to defy its own rules, as long as no real information crosses that sacred boundary. Another way to think about this is through the concept of influence. Physics forbids faster-than-light influence, meaning one event cannot cause another outside its light cone, the region of spacetime reachable by signals traveling at or below the speed of light. Even if some abstract mathematical description allows a quantity to change instantaneously, it doesn't mean one place is influencing another in a physically meaningful way. For instance, in certain quantum systems, correlations between particles can appear instantly across space, but no usable message is actually being sent. The information, what you could, in theory, use to communicate or trigger a change, remains constrained by light speed. This subtlety explains why physicists are cautious when people claim something has moved faster than light. They immediately ask, was information transferred? If the answer is no, then relativity remains intact. The appearance of superluminal, faster-than-light behavior might just be an illusion of the system's structure or the way we measure it. For instance, when we observe distant galaxies receding from us faster than light due to the universe's expansion, no signal is actually moving through space at that speed. It's space itself stretching, carrying galaxies along. There's a famous analogy used in relativity education. Imagine ants walking on the surface of an expanding balloon. The ants represent light or signals, moving locally along the balloon's surface at a fixed speed. If the balloon inflates, two ants on opposite sides will find themselves separating faster than they can crawl. But that doesn't mean either ant has broken their speed limit. The expansion of space itself allows apparent superluminal separation without violating relativity or causality. Similarly, in many physical systems, structures or patterns can outrun light, but not the actual transmission of new cause-effect information. This distinction has profound implications for how we interpret experiments that seem to hint at faster-than-light behavior. It tells us that physics doesn't forbid everything from exceeding the speed of light. It forbids communication or energy transfer from doing so. In fact, many natural phenomena give the illusion of superluminal motion when viewed from certain perspectives. For example, when a laser pointer sweeps across the surface of the moon, the bright dot moves faster than light across the lunar surface. But that's just geometry. No single photon, no actual signal, traveled across that distance faster than light. The dot's apparent motion is simply the result of the beam's direction changing over a huge distance. This concept also helps us avoid common misconceptions about so-called instantaneous effects in physics. For instance, in classical electromagnetism, the change in an electric field when you move a charge isn't felt instantly everywhere. It propagates outward at the speed of light. If that weren't true, it would mean information about the movement of the charge could reach distant places instantaneously violating relativity. The laws of physics carefully maintain that any change that carries new information must travel no faster than light. Understanding this boundary is what allows modern physics to balance flexibility with consistency. The universe leaves room for fascinating, seemingly paradoxical phenomena: wave patterns that outpace light, correlations that appear instantaneous, cosmic expansions that stretch beyond any speed limit. Yet all of them respect the one unbreakable law: no information can move faster than light. So while certain things can appear to move faster than light, or even mathematically exist at those speeds, the communication of cause and effect always stays within light's reach. The cosmos may flirt with illusion, but it never truly betrays its own logic. This principle will become even clearer as we move into the next concept: how wave systems, through their phase and group velocities, can mimic faster-than-light behavior without actually transferring any information at all. When we dive deeper into the physics of waves, especially light waves and electromagnetic fields, we encounter two fascinating and often confusing concepts: phase velocity and group velocity. These two terms describe different aspects of how waves move through space, and they're crucial to understanding why some things can appear to move faster than light without actually violating the laws of physics. Every wave can be thought of as a combination of many oscillations, each with its own wavelength and frequency. The phase velocity is the speed at which a particular point on the wave, say the crest, appears to move. It's the rate at which the phase of the wave propagates through space. Mathematically, it's defined as Vp equals omega over k, where omega is the angular frequency and k is the wave number. In some materials, particularly those that are dispersive, meaning their refractive index depends on frequency, this phase velocity can actually exceed the speed of light in a vacuum. This might sound like a direct violation of relativity, but it isn't. The key is that the phase velocity doesn't carry any information or energy by itself. It's just a visual representation of how the wave's oscillations line up in space and time. You could think of it like a rotating pattern of lights. The individual bulbs don't move, but the bright spots in the pattern appear to travel faster than any single bulb could. The wave crests are a pattern, not a physical signal. Now, the group velocity is a different story. It represents the speed at which the overall envelope of the wave, essentially the packet that contains the actual energy or information, moves. If you were to send a pulse of light through a medium, the leading edge of that pulse, its group velocity, is the part that can convey new information. In most physical systems, this group velocity always stays below or equal to the speed of light. That's because the group velocity corresponds to the flow of energy and cause and effect relationships. However, the real world adds some wrinkles. In certain exotic materials or under very specific laboratory conditions, scientists have observed superluminal phase velocities and even group velocities greater than light speed. These effects occur in regions called anomalous dispersion, where the medium's refractive index changes rapidly with frequency. In these cases, the peak of a wave packet might appear to exit the medium before it fully enters, creating the illusion of faster-than-light transmission. But when physicists analyze the situation closely, they find that the front of the pulse, the part that carries genuinely new information, still obeys the light speed limit. What's happening is that the pulse's shape is distorted, often with parts of the wave being amplified or suppressed in such a way that the overall peak shifts forward. No information is actually being transmitted faster than light. It's just a trick of interference and signal reshaping. An intuitive analogy helps. Imagine a line of people performing the wave in a stadium. The motion of the wave appears to travel rapidly around the arena, and in principle, if the crowd were big enough and coordinated enough, that pattern could seem to move faster than light. but no single person moves at that speed. Each only lifts their arms up and down. The appearance of speed is just a coordinated pattern, not the physical motion of anything tangible. Similarly, when a light wave's phase appears to move faster than light, it's just the pattern of oscillation shifting. It doesn't represent a physical transmission of energy or data. In more advanced physics, this concept is tied to signal velocity, which is the true measure of how fast a causal influence can move. The signal velocity, unlike the phase or group velocity, marks the speed of the very first detectable change in a system, the front of the wave that carries new information. And experiments have repeatedly confirmed that this signal velocity never exceeds the speed of light in a vacuum. One of the most famous demonstrations of this principle came from experiments in the late 1990s and early 2000s, when scientists used carefully engineered materials called gain-assisted media to make light pulses appear to move faster than light, or even travel backward in time over short distances. In those cases, the peak of the light pulse exited the medium before the peak of the same pulse entered it. This astonishing result seemed to defy everything we know about causality. But a deeper analysis revealed that no part of the pulse containing new information actually traveled faster than light. The superluminal effect was caused by reshaping. The tail of the pulse inside the medium interfered constructively with its leading edge, making the peak appear to jump forward. The true front of the pulse, which carries the first hint of a signal, still obeyed relativity. This interplay between phase, group, and signal velocities is one of the reasons physicists are so careful when they talk about faster-than-light motion. It shows that our perception can be easily deceived by the mathematics of waves, especially when we deal with complex systems like electromagnetic fields or quantum waves. What's moving faster than light isn't the information, it's the pattern, the interference, the mathematical description. The physical reality, the energy, the message, the cause, never outruns light. And this brings us closer to one of the most mysterious and captivating ideas in modern physics: quantum entanglement. Because if wave interference shows us how patterns can appear to outpace light without violating causality, entanglement goes one step further. It seems to let particles communicate instantaneously across vast distances. But as we'll soon see, even in that strange quantum realm, nature's ultimate speed limit still holds firm in surprising and subtle ways. Quantum entanglement stands as one of the most intriguing, counterintuitive, and frequently misunderstood phenomena in all of physics. It is often invoked in conversations about faster-than-light communication, and at first glance, it appears to defy Einstein's cosmic speed limit completely. When two particles become entangled, their quantum states become linked in such a profound way that measuring one particle seems to instantly determine the state of the other, no matter how far apart they are. Einstein himself famously called this spooky action at a distance, because it appeared that information was somehow leaping across space instantaneously. To understand what makes this so puzzling, we need to look at what entanglement really is. In quantum mechanics, particles such as electrons or photons can exist in a superposition, meaning they don't have definite properties until they are measured. For instance, an electron might be said to be spinning both up and down simultaneously until we observe it. When two particles interact and become entangled, their properties become correlated. This means that if one particle is later measured and found to be spin up, the other must be spin down, even if they're light years apart. This instant correlation seems to suggest that some kind of signal passes between the two particles faster than light. But that's not what's actually happening. The key lies in the nature of quantum measurement. When we measure one particle's property, we aren't sending any message or signal to the other particle. The measurement outcome is inherently random. It's not determined until the act of measurement occurs. Once you measure one particle and get a random result, the state of the other particle is simply consistent with that outcome, because they were entangled from the start. No usable information is transmitted from one location to another at that moment. A simple analogy might help. Imagine two playing cards, one red, one black, are shuffled, sealed in envelopes, and sent to two distant people. Until one person opens their envelope, neither knows which card they have. When the first person opens it and sees red, they immediately know the other person's card must be black. Did information travel instantly across the distance separating them? Of course not. The correlation was already built in when the cards were sealed. The instant realization is just the act of uncovering what was already true. Quantum entanglement, however, is more subtle than the playing card example, because the quantum world doesn't merely hide pre-existing values waiting to be revealed. The entangled particles don't have definite states until they're measured, and yet their outcomes are perfectly correlated once measured. That's what gives the phenomenon its eerie quality. But even then, these correlations can't be used to transmit a message or influence the distant particle in a controllable way. The outcome on one side is random, and randomness cannot carry structured information. To send an actual message faster than light, you would need to control what result appears when you measure your particle, and that's impossible according to quantum theory. The results are probabilistic. Even if two observers measure their entangled particles at exactly the same time, each will get random outcomes individually. It's only after they compare their results, by sending data through normal, light-speed limited channels, that the correlation becomes evident. Until then, neither observer can distinguish whether their particle is entangled or not. This point is essential. Quantum entanglement produces correlations, not communication. The entangled connection ensures that the universe maintains internal consistency between the two particles' measurements, but it doesn't allow one observer to send a signal to the other. The universe, in a sense, already knows how the two outcomes will align, even though it doesn't determine the specific results until measurement. The appearance of instant connection is a reflection of the deep mathematical unity of the entangled system, not a violation of the speed of light. Physicists have tested this repeatedly in the laboratory. The most famous of these are Bell test experiments, which measure correlations between entangled particles over large distances. Decades of increasingly precise tests have confirmed the strange, non-local correlations predicted by quantum mechanics. But every experiment also confirms that no information actually travels faster than light. The two particles behave as if they share a single quantum description spread out in space, not as if one is sending a message to the other. Some modern interpretations of quantum mechanics, such as the many worlds interpretation, even remove the need to imagine communication between particles entirely. In these views, the universe's wave function encompasses both particles as one combined system. When a measurement happens, both outcomes occur in separate branches of reality, maintaining consistency across the whole without any signal transmission at all. Others, like the pilot wave theory, interpret the connection as deterministic, but still constrained by relativity when it comes to transferring usable information. In all interpretations, though, the conclusion remains the same. Entanglement does not let us send signals faster than light. It may seem as though the two particles know about each other instantly, but this knowing is not an exchange of data. It's a reflection of shared origin and structure. The quantum world plays by rules that are alien to our intuition, but even here, the cosmic speed limit holds steady. So while quantum entanglement has given rise to sensational headlines about instant communication or quantum teleportation, the reality is subtler and far more fascinating. It shows us that the universe can be deeply interconnected in ways that transcend our classical notions of space and time, without ever breaking the principles that make reality consistent. In the next segment, we'll explore why these correlations, so instantaneous and mysterious, still don't equate to faster-than-light communication, and how the details of quantum measurement ensure that even this spooky action stays firmly within relativity's bounds. To truly understand why quantum entanglement doesn't allow faster-than-light communication, we need to look carefully at what happens during a quantum measurement. The key misunderstanding arises from a natural but misleading intuition. When one particle in an entangled pair is measured, the other instantly knows how to respond, no matter how far away it is. At first glance, this looks like instantaneous communication. But the truth is, no data, no signal, and no controllable message is actually being sent. When two particles are entangled, their quantum states are not separate. They form one unified quantum system described by a single mathematical wave function. This means that before measurement, the particles don't possess definite individual properties. Instead, they share a combined state that contains all the possible outcomes as probabilities. Once one of the particles is measured, the wave function collapses, assigning definite properties to both particles. But crucially, this collapse doesn't represent a transmission of information through space. It's a global update to the entire mathematical description of the system. Think of it like updating a spreadsheet stored in the cloud. If you change a cell on one device, the spreadsheet updates everywhere at once. But that's because it's a single shared file, not because one computer sent a signal faster than light to the other. Similarly, in quantum mechanics, the entangled particles aren't separate entities trading messages. They are two parts of one extended quantum object. The instantaneous change we observe is a reflection of that unity, not a cause and effect communication between distant points in space. Now, imagine two scientists performing an experiment with entangled photons. One is on Earth and the other is on Mars. Each scientist measures the polarization of their photon, getting random results of either horizontal or vertical. The observer on Earth sees only a random sequence, up, down, completely unpredictable. The scientist on Mars sees a random sequence too, also unpredictable. Neither observer can infer anything about the other's results without exchanging data. It's only after they later share their measurements, using a conventional communication method limited by light speed, that they notice something remarkable. The results are perfectly correlated. When one saw up, the other always saw down. This is the heart of the matter. The correlation between outcomes becomes evident only when the two sets of results are compared later, through an ordinary information channel that obeys relativity. Until then, each observer's data looks purely random. If one could somehow control the outcome of their measurement, say, choose whether their photon turns out up or down, then yes, they could encode a message and send it instantly to the other side. But quantum mechanics doesn't allow that control. The outcomes are fundamentally probabilistic, determined only at the moment of measurement. You can't force your particle to take a specific state, and therefore you can't encode or transmit information this way. To put it simply, entanglement correlations are not communications. They're coincidences enforced by the laws of quantum mechanics. Coincidences that remain hidden until classical data, traveling at or below the speed of light, reveals them. This is what physicists mean when they say that entanglement shows non-local correlations, but not non-local causation. The correlations seem to transcend distance, but no cause or signal is moving faster than light. Einstein himself wrestled with this idea. He objected to the notion of instantaneous effects, arguing that quantum mechanics must be incomplete. Perhaps there were hidden variables determining outcomes behind the scenes. But experiments over the last few decades, most famously those testing Bell's inequalities, have shown that no local hidden variable theory can explain entanglement. The correlations are real, but they still don't carry information. The universe allows connections that defy classical intuition, yet it forbids us from exploiting them to send messages faster than light. Even in advanced technologies like quantum teleportation, where an unknown quantum state can be transmitted from one location to another using entanglement, FTL communication remains impossible. Teleportation requires two components: an entangled pair shared between sender and receiver, and a set of classical instructions that must be sent through normal, light-speed limited channels. Without that classical communication, the receiver cannot reconstruct the transmitted quantum state. Once again, relativity remains undefeated. The deeper lesson here is that nature seems to draw a very clear line between correlation and communication. Entanglement shows us that reality is far more interconnected than our senses perceive. Two particles can remain linked across billions of kilometers, their properties tied together in a way that transcends spatial distance. But this linkage doesn't allow us to cheat time or distance. The universe ensures that the integrity of cause and effect remains intact, no matter how strange the quantum world becomes. So while entanglement captures the imagination as a possible loophole in Einstein's cosmic speed limit, it's not the key to faster-than-light messaging. What it truly reveals is the profound depth of quantum reality, that everything in the universe may be connected at a level beyond classical understanding. Yet even in that connectedness, the laws of causality stand unbroken. And as we continue exploring the possibility of faster-than-light phenomena, we step from the verified world of quantum mechanics into the speculative domain of hypothetical particles. Beings that would, by definition, always travel faster than light. These are known as tachyons, and they challenge the very foundations of physics in ways that are as mind-bending as they are paradoxical. In the quest to understand whether anything could truly move faster than light, physicists have long speculated about a class of hypothetical particles called tachyons. The name comes from the Greek word tachys, meaning swift, and the idea behind them is simple yet extraordinary. If ordinary particles, like electrons and protons, can only move slower than light, then perhaps tachyons are their mirror opposites, existing only at speeds greater than light. Unlike normal matter, which would need infinite energy to reach light speed, tachyons could never slow down to or below it. They would forever remain in the superluminal realm, forever faster than light. The concept of tachyons was first proposed in the 1960s as physicists explored the mathematical possibilities hidden within Einstein's special relativity. According to relativity, the energy of an object increases as it moves faster, approaching infinity at light speed. However, if one plays with the equations and imagines a particle already beyond that barrier, something strange happens. Its energy becomes imaginary, in the mathematical sense, involving the square root of a negative number. Rather than having real, positive mass, a tachyon would have what's called imaginary mass, a quantity that cannot exist in the real, physical sense we're familiar with. This makes tachyons fascinating, but also deeply problematic for our understanding of physics. In theory, tachyons could move at any speed faster than light, 10 times, 1,000,000 times, or even infinitely faster. They would slow down as they gain energy, rather than speeding up, which completely inverts the behavior of normal matter. The more energy a tachyon loses, the faster it would move. This property alone highlights just how alien such particles would be to our universe's logic. It's as though the arrow of cause and effect would bend in strange ways for them, existing in a reversed framework compared to everything else we know. Because of these bizarre characteristics, tachyons have remained entirely theoretical. No experiment has ever detected one, and there's no empirical evidence that they exist. Scientists have searched for their potential fingerprints in high-energy cosmic rays, particle accelerators, and nuclear reactions, but every test has come up empty. The reason isn't just technological limitation, it's conceptual. If tachyons truly existed, they would violate several key principles of modern physics, including energy conservation and causality. Even detecting one would be nearly impossible, since any interaction it has with normal matter would theoretically release infinite energy due to the mismatch between subluminal and superluminal states. Despite the lack of evidence, tachyons have held an enduring place in both theoretical physics and science fiction because they represent a tantalizing what if. They are often used as storytelling devices to explain things like instantaneous communication, time travel, or faster-than-light propulsion. In some science fiction worlds, like Star Trek, tachyon particles are invoked as carriers of faster-than-light signals or as components in exotic technologies. While purely speculative, these ideas capture a real sense of scientific curiosity about what might exist beyond our current comprehension. Interestingly, tachyons also appear occasionally in the realm of advanced theoretical physics, not as physical particles, but as mathematical tools. In certain versions of quantum field theory and string theory, tachyon-like terms can appear in equations, signaling an instability in the system rather than the existence of real, faster-than-light particles. In these contexts, tachyons are not entities that zoom through space, but indicators that a given state of a physical field is unstable and will quickly decay into a more stable configuration. Once that instability resolves, the tachyonic behavior disappears and normal physics resumes. Still, the mere mathematical possibility of tachyons raises profound questions. If something could exist beyond light speed, what would that mean for causality and time? How would it interact with the rest of the universe? Could we even detect its presence if it exists in a domain fundamentally disconnected from our own? These questions lead naturally into the deeper paradoxes that tachyons imply. Paradoxes that challenge the very consistency of space, time, and the logical flow of cause and effect. For now, tachyons remain a powerful symbol of curiosity and imagination. They remind us that the boundary set by light speed isn't just a technological challenge, it's a conceptual horizon. Beyond it lies a realm of ideas that stretch the limits of logic itself. And as we'll explore next, if tachyons were ever to exist, they wouldn't just move faster than light. They would also invite some of the strangest paradoxes in all of physics, including the possibility of sending messages backward in time. If tachyons were real, if something could truly move faster than light, the consequences would ripple far beyond just faster communication or travel. They would undermine one of the most fundamental pillars of physics, causality, the simple rule that causes come before their effects. It's the foundation of logic itself. Throw a stone, and only after you throw it does the window break. Strike a match, and only afterward does the flame appear. But if tachyons existed and could transmit information or interact with normal matter, this natural order could collapse. To see why, we need to revisit what Einstein's theory of relativity tells us about how space and time behave at high speeds. In relativity, there is no universal, absolute sense of now. Two events that appear simultaneous to one observer might occur in a different order for someone moving at a different speed. This relativity of simultaneity doesn't matter for sublight signals, because all of them stay within a common cause and effect structure. But if something could move faster than light, then for some observers, it would appear to move backward in time. Let's imagine a simple thought experiment. Suppose you have a tachyon transmitter capable of sending a signal to a friend on a distant planet. From your perspective on Earth, you send the tachyon message at noon, and it arrives at their location a few seconds later, appearing to travel faster than light. So far, so good. Just a faster message. But according to an observer moving relative to you, special relativity says the order of events might flip. From their frame of reference, the signal might arrive before it was sent. In other words, your friend would receive the message before you even pressed send. That alone sounds strange, but the paradox deepens when we add a second step. Imagine your friend immediately replies with their own tachyon signal back to you. Depending on the speeds and directions involved, you might receive their reply before you sent your original message. The result is a closed causal loop, an event where the effect, receiving the reply, happens before its cause, sending the message. This kind of loop breaks the very concept of cause and effect, producing paradoxes that even logic itself can't untangle. Physicists often illustrate this using the tachyonic anti-telephone, a theoretical device that uses tachyons to send messages backward in time. It's not just a wild science fiction fantasy. It's a genuine consequence of the math of relativity if faster-than-light signaling were possible. The tachyonic anti-telephone would let two observers in relative motion exchange messages in such a way that each one receives a reply before the other sends it. This kind of feedback loop creates what's called a causality violation. It means you could, in principle, send information to your own past. And from there, the paradoxes multiply. Imagine warning your past self about an event, preventing it from happening, which means you never sent the warning in the first place. This is the grandfather paradox in a new disguise: actions that prevent their own causes. In a universe where tachyon communication is possible, logic itself would start to fracture. Events could exist without causes, outcomes could appear spontaneously, and the sequence of time could no longer be trusted. This is why most physicists consider the existence of tachyons incompatible with a self-consistent reality. The entire structure of relativity depends on the preservation of causality. Once that link breaks, the laws of physics would lose their predictive power. If an effect can precede its cause, then the universe becomes a paradox machine where anything and everything could happen without reason. Even in mathematical models that include tachyon-like behavior, such as certain quantum field theories, physicists carefully redefine what tachyon means to avoid these paradoxes. There, tachyons represent instabilities, signals that a system is in an unstable state and will rapidly decay into a more stable one, rather than particles actually moving faster than light. This reinterpretation ensures that no real information or energy travels backward in time. The deeper message is that the laws of physics are not just about speed, they are about consistency. Every rule, from relativity to quantum mechanics, seems to conspire to protect causality at all costs. Even in the wildest corners of theoretical physics, nature appears to reject anything that would allow messages from the future to influence the past. Tachyons, if they ever existed in a form that could carry information, would therefore threaten the logical coherence of space-time itself. This is why many scientists believe that the universe has built-in safeguards, cosmic speed limits, and the structure of space-time to prevent paradoxes like these. The light speed barrier isn't just about how fast you can go. It's about maintaining the direction of cause and effect, keeping the arrow of time intact. Yet, even with tachyons ruled out as messengers or travelers, physicists haven't stopped exploring ways to outmaneuver light speed, not by breaking it, but by bending the structure of space-time itself. Instead of moving through space faster than light, what if we could make space move around us? That question leads us directly to one of the most audacious ideas in theoretical physics: the concept of warp drives and space-time manipulation. The idea of a warp drive sits at the crossroads of science fiction and theoretical physics, a dazzling concept that dares to ask, if nothing can move through space faster than light, what if we could make space itself do the moving? That's the core principle behind Miguel Alcubierre's 1994 proposal of the Alcubierre drive, a legitimate solution to Einstein's equations of general relativity. It doesn't break relativity's rules, rather, it cleverly bends them. In simple terms, the Alcubierre drive doesn't propel a spacecraft forward like a rocket. Instead, it manipulates the very fabric of space-time surrounding it. Imagine space as a flexible fabric that can be stretched or compressed. The drive would work by compressing space in front of the ship and expanding space behind it, creating a kind of space-time wave that carries the ship forward. The craft itself would sit in a bubble of flat space-time, completely stationary relative to the space immediately around it, while the bubble moves faster than light relative to distant observers. This is a profound distinction. Within the bubble, the ship and its passengers aren't breaking any physical laws. Locally, they're at rest, feeling no acceleration and never exceeding light speed. It's the bubble of space-time that moves, not the ship through space-time. Because relativity's speed limit only applies to motion within space-time, not to the motion of space-time itself. The warp drive doesn't technically violate Einstein's rules. It's like surfing a wave rather than swimming through the ocean. The surfer stays still relative to the wave, even though the wave moves swiftly across the sea. Einstein's field equations describe how matter and energy shape the geometry of space-time. So in principle, if you could find the right distribution of energy, you could produce such a warp bubble. Alcubierre worked out the mathematics showing that such a configuration is theoretically possible. In his model, the equations allow a region of space-time to contract and expand in the necessary way, creating a faster-than-light effect without the ship itself exceeding the light speed barrier. However, there's a monumental catch. The kind of energy required to make it work doesn't exist in any form we can currently produce. The Alcubierre drive would require negative energy density, a form of exotic matter that has less than zero energy. Ordinary matter, like the stuff that makes up stars and planets, has positive energy density and curves space-time in the familiar way that creates gravity. Negative energy, on the other hand, would curve space-time in the opposite direction, repelling rather than attracting. This exotic energy would be necessary to create the expanding and contracting regions of space-time that make the warp bubble possible. Negative energy isn't entirely fictional, though. Certain quantum effects, like the Casimir effect, demonstrate that negative energy densities can exist in very small, fleeting amounts. When two metal plates are placed extremely close together in a vacuum, quantum fluctuations create a slight pressure difference that behaves as if there's negative energy between the plates. It's a tiny effect, barely measurable, but it shows that the laws of physics don't outright forbid negative energy. The challenge is that the Alcubierre drive would need a colossal amount of it, possibly more energy than exists in the entire observable universe, to move even a small spacecraft. Beyond the energy problem, there are other enormous theoretical hurdles. For example, how would you create or control the warp bubble in the first place? How would you steer it or stop it once it's in motion? Some models suggest that anything inside the bubble would be causally disconnected from the space outside it, meaning you couldn't send a signal forward to control where you're going. In essence, you could start the drive, but you'd have no way to stop or navigate it until it naturally decayed. Then there's the issue of radiation. Studies have shown that as a warp bubble moves, it could accumulate high-energy particles along its boundary. When the bubble slows down or collapses, that energy could be released in an intense burst, enough to obliterate anything in its path. So even if you could create a warp drive, it might be catastrophically dangerous to use. Despite these seemingly impossible challenges, physicists continue to study warp metrics because they push the boundaries of our understanding. They force us to ask what relativity truly allows, and whether space-time can be manipulated in ways we haven't yet imagined. In recent years, researchers have proposed refinements to Alcubierre's original model that reduce the energy requirements, still immense, but perhaps not infinite. Some theoretical designs suggest using alternative space-time geometries or quantum field effects to make the concept slightly more feasible. What makes warp drives so captivating is that they don't break the rules, they exploit them. They reveal that the speed of light limit applies only locally within space-time, and that by reshaping space-time itself, one could, in principle, go anywhere at any apparent speed without ever truly moving. It's a perfect example of how the universe's most rigid laws can sometimes bend in the most unexpected ways. Still, warp drives remain purely speculative. They exist only on paper, within equations that dance delicately between the possible and the impossible. But they represent something profoundly human: our refusal to accept limits without first testing them. And as we follow this thread of bending space-time, we encounter another equally captivating idea, one that might not stretch space but connect distant points directly: wormholes. The concept of wormholes takes the dream of faster-than-light travel to another level, not by moving through space at impossible speeds, but by taking a shortcut through the fabric of space-time itself. While warp drives stretch and compress space to move a bubble forward, wormholes fold space in such a way that two distant points become directly connected. If such a structure could exist, you wouldn't need to break the light speed barrier at all. You'd simply step through from one end to the other, covering vast cosmic distances in an instant. The idea of wormholes arises naturally from Einstein's general theory of relativity. In 1935, Einstein and his colleague Nathan Rosen discovered a mathematical solution to Einstein's equations that connected two separate regions of space-time via a bridge. This came to be known as the Einstein-Rosen bridge, the first theoretical model of a wormhole. To visualize it, imagine space as a two-dimensional sheet of paper. Normally, to travel from one point to another, you must move along the surface, following the curve of the paper. But if you fold the paper so that the 2 points touch, then puncture a hole between them, you can pass directly through. That tunnel connecting the points, that's what a wormhole is. In relativity, space-time can curve, twist, and warp depending on the presence of mass and energy. A wormhole would be an extreme curvature, a tunnel-like geometry linking two distant regions of space, or even time. The entrance and exit of this tunnel are called mouths, and the interior passage is the throat. Theoretically, if one could keep the throat open and stable, it might be possible to travel between the mouths almost instantaneously, even if they were light years apart. From the outside, it would appear as though you'd traveled faster than light. But locally, inside the wormhole, you'd never exceed light speed. You'd simply take a shorter route through space-time. This is what makes wormholes so fascinating. They provide a possible loophole to the cosmic speed limit without actually violating it. Light speed travel is still respected locally. Nothing moves faster than light within the tunnel itself. Yet, the global structure of space-time is altered in such a way that you can emerge somewhere far away almost instantly. From a relativistic standpoint, the rule isn't broken, it's cleverly sidestepped. However, as elegant as the mathematics is, reality introduces a serious set of complications. Most naturally occurring wormhole solutions to Einstein's equations are unstable. A traversable wormhole, one that a spacecraft or human could safely pass through, would collapse faster than light could travel through it, closing before anything could cross. The gravitational forces around the throat would be so immense that anything entering it would be torn apart by tidal forces. In essence, relativity allows wormholes in theory, but it gives them a very short lifespan, too short to be useful. Physicists like Kip Thorne, who popularized the idea of traversable wormholes and consulted on the movie Interstellar, showed that to keep a wormhole open,
you would need exotic matter with negative energy density, much like the material required for a warp drive. Negative energy would act as an anti-gravity force, counteracting the immense pressure that would otherwise collapse the wormhole. Once again, though, this type of energy is purely theoretical. While quantum effects such as the Casimir effect suggest negative energy can exist on microscopic scales, there's no evidence it can be harnessed or sustained in the quantities needed for macroscopic wormholes. Even if a stable wormhole could exist, it would come with additional puzzles. For instance, depending on how its two mouths move through space and time, a wormhole might not only connect two distant locations, but also two different points in time. This opens the door to potential time travel paradoxes. By moving one mouth at relativistic speeds and bringing it back, you could, in principle, create a time difference between the ends, turning the wormhole into a time machine.
Physicists like Stephen Hawking argued that such configurations could violate causality, leading to paradoxes where effects precede their causes. To protect the consistency of reality, Hawking proposed the chronology protection conjecture, the idea that the laws of physics prevent time loops from forming in the first place, possibly by destroying any wormhole that could lead to one. Beyond causality, wormholes face daunting practical barriers. Even if one could be created or found, keeping it open would require an impossible degree of control over space-time curvature. The gravitational energy near the throat could destroy anything passing through, and the slightest fluctuation in energy could destabilize the entire structure. Some theories suggest quantum effects might cause the wormhole to collapse into a black hole or explode into radiation before it could ever be used. Yet the allure of wormholes persists because they elegantly illustrate how relativity doesn't just describe space. It gives us the power, at least theoretically, to reshape it. They serve as a tantalizing reminder that the universe may be far stranger and more interconnected than our everyday experience suggests. In the same way that Einstein's equations predicted black holes long before we found evidence of them, wormholes remain as mathematical possibilities, waiting for the right physical insight, or perhaps a new understanding of quantum gravity, to determine whether they're real or just beautiful fiction. Still, whether wormholes ever prove to be real or not, they share a theme with warp drives and tachyons. They challenge the light speed limit not by ignoring it, but by exploring the loopholes built into the geometry of space-time itself. But all these concepts, warp bubbles, exotic matter, and wormholes, run into the same ultimate wall: energy. The universe demands unimaginable amounts of it to bend its structure this way, far beyond anything humanity can hope to produce with known physics. And so, before we imagine walking through wormholes or surfing space-time waves, we must confront a more grounded question. What would it actually take to power such feats? And is there any realistic hope of achieving it? While concepts like warp drives and wormholes are dazzling glimpses into what the universe might allow in theory, they also confront us with an unavoidable truth. The energy demands of such space-time manipulation are staggering, so enormous that they currently exist well beyond the reach of human technology, and perhaps even beyond what nature itself can practically allow. The mathematics of relativity tells us that these ideas don't explicitly break the rules of physics, but they operate on the razor's edge of those rules, requiring ingredients that are, for all intents and purposes, impossible to obtain. The biggest challenge is the requirement for exotic energy, particularly negative energy density. In normal physics, energy is always positive. Mass and radiation contribute to the curvature of space-time in predictable ways, creating gravity that attracts. Negative energy, however, does the opposite. It would repel, stretching space-time outward rather than compressing it inward. Both warp bubbles and traversable wormholes rely on this repulsive effect to stabilize the geometry they need. Keeping a wormhole throat open or allowing a warp bubble to expand space behind it and contract space in front. Without negative energy, the structure collapses under its own gravity almost instantly. But here's the catch. Negative energy isn't something we can simply generate or store. In everyday physics, it doesn't exist as a usable form of matter or fuel. It's only hinted at indirectly through rare quantum effects. The most famous of these is the Casimir effect, where two uncharged, parallel metal plates placed very close together in a vacuum experience a tiny attractive force. This occurs because quantum fluctuations in empty space are restricted between the plates, creating a small region of lower energy density. Essentially, a pocket of negative energy compared to the surrounding vacuum. It's real, measurable, and a profound demonstration that space itself seethes with quantum activity. Yet the Casimir effect is infinitesimally weak. The amount of negative energy generated between the plates is vanishingly small, billions of times too tiny to influence space-time on any meaningful scale. To stabilize even a microscopic wormhole or power a minuscule warp bubble, you'd need an energy density many orders of magnitude greater than anything the Casimir effect provides. Physicist Kip Thorne once estimated that keeping a wormhole just a few meters wide stable might require negative energy equivalent to the mass of an entire star. For an Alcubierre drive, early estimates suggested the energy of the entire visible universe might be required just to move a modest spacecraft. Although later refinements to the Alcubierre model reduced these requirements somewhat, they remain absurdly high. Even optimistic calculations propose needing the mass energy of Jupiter or more, compressed into exotic forms of space-time curvature that we have no mechanism to control. The physics is sound in theory. It follows the equations of general relativity, but the practicality is utterly beyond imagination. It's as if nature itself permits the loophole, but hides the key behind insurmountable barriers. Then there's the issue of stability and containment. Suppose for a moment that we somehow discovered a way to generate negative energy. How would we handle it? Negative energy would behave in fundamentally counterintuitive ways. Rather than attracting normal matter, it would repel it, possibly destabilizing anything nearby. It could interact destructively with normal fields, creating unpredictable effects or catastrophic instabilities. Even if it could be confined safely, the precision required to shape space-time geometry, to hold open a wormhole or maintain a warp bubble, would demand control over gravity and quantum fields at a level of mastery far beyond our current understanding. Furthermore, quantum theory may impose limits that prevent large-scale negative energy from ever accumulating. According to what's known as quantum inequality constraints, negative energy can only exist in tiny amounts and for very short durations. These constraints act like nature's safety net, preventing violations of causality or the creation of paradoxical phenomena such as perpetual motion or time loops. If these constraints hold true universally, then stable wormholes and warp drives aren't just impractical, they're fundamentally forbidden by the quantum fabric of reality itself. Even aside from negative energy, the sheer scale of power required to manipulate space-time is staggering. Bending space-time noticeably requires energy comparable to the mass of planets. Every time we curve space-time, even slightly, we're fighting against the colossal rigidity of the universe's geometry. The energy stored in just 1 kilogram of matter, E equals mc squared, is about 9 times 10 to the 16th joules, roughly equivalent to the energy released by a 21 megaton nuclear explosion. Yet even if we converted entire planets into usable energy, it still wouldn't be enough to warp or tunnel through space in any meaningful way. This enormous gap between theory and practice highlights an important truth. Relativity doesn't make faster-than-light travel impossible. It makes it inaccessible under the laws of known physics. It's as if the universe teases us with mathematical possibilities, but the practical toll is so extreme that no civilization bound by ordinary matter and energy could pay the price. Still, the allure of these ideas persists, not because they are practical, but because they stretch the limits of human imagination. They remind us that our understanding of energy, matter, and space-time is still incomplete. Perhaps, buried within quantum gravity or some yet unknown theory, there are mechanisms that make such feats achievable on scales we can't yet comprehend. For now, though, warp drives and wormholes remain as thought experiments, beautiful, haunting demonstrations of the power and precision of Einstein's equations. They show that physics does not close the door entirely. It simply makes the handle nearly impossible to reach. But even without exotic space-time engineering, scientists have found curious ways to make light itself seem to move faster than its own cosmic limit, at least in the laboratory. These experiments, while not breaking the rules of relativity, reveal just how slippery and surprising the nature of light can be. Over the past few decades, scientists have conducted a series of remarkable experiments in laboratories that appear, at first glance, to challenge one of the universe's most sacred limits: the speed of light. These experiments involve pulses of light, brief bursts of electromagnetic energy, that seem to travel faster than light itself, or in some cases, even emerge from a medium before they've fully entered it. When the first of these results were published, they caused quite a stir, with headlines proclaiming that Einstein's relativity had been broken. But the deeper truth is both subtler and far more fascinating. These experiments don't actually send information faster than light. Instead, they reveal the strange ways light behaves when it interacts with complex materials and the clever illusions that can arise when waves overlap and reshape themselves. One of the earliest and most famous examples came from physicists Lijun Wang and Alexander Kuzmich at the NEC Research Institute in 2000. They sent a carefully shaped laser pulse through a chamber of specially prepared cesium gas and observed that the peak of the pulse exited the chamber before the main part of the pulse had even finished entering it. In effect, it looked as though the light pulse had traveled thousands of times faster than the speed of light in a vacuum. The results were astonishing, but not, as it turned out, revolutionary in the sense of overthrowing relativity. To understand why, we need to revisit the distinction between different kinds of speed that describe wave motion: phase velocity, group velocity, and signal velocity. The phase velocity describes how individual wave peaks move, while the group velocity refers to how the overall envelope, the shape of the wave packet, propagates through space. The signal velocity, on the other hand, is the true measure of how fast information or energy travels. What these faster-than-light experiments showed is that while group velocity can appear to exceed the speed of light under certain conditions, signal velocity never does. In the case of the NEC experiment, the cesium gas created a region of anomalous dispersion, where the refractive index of the medium changed very rapidly with frequency. This caused parts of the light wave spectrum to interfere in such a way that the shape of the pulse became distorted. The front of the pulse was amplified, while its back was suppressed. The result was that the peak of the pulse seemed to jump ahead, creating the illusion that the light had outrun itself. But this was not a real transmission of information. The actual front of the pulse, the very first point where light begins to rise from zero, never exceeded the speed of light. It is this front that carries any new information, and in every experiment ever performed, that boundary remains faithful to Einstein's limit. To visualize this, think of a crowd at a concert doing the wave. The crest of the wave, the part that catches your eye, can appear to move faster or slower depending on how people time their motion. You could even make the crest appear to leap forward if people in one section stand slightly earlier than expected. But no single person moves faster than their own reaction time allows. The apparent speed of the pattern doesn't correspond to any real transfer of matter or energy. Similarly, in these optical experiments, the pattern of the light wave changes, but the underlying information encoded within it does not leap ahead. Other experiments have demonstrated related effects, including fast light and slow light phenomena. In slow light experiments, researchers have managed to reduce the apparent speed of light to just a few meters per second, so slow that a light pulse can literally be stopped and stored temporarily in an atomic gas before being released again. Fast light experiments are the mirror image of this. The pulse appears to speed up, and in extreme cases, its peak exits the medium before it logically should. Both effects arise from the same underlying principle, dispersion engineering, where the properties of the medium cause certain frequencies of light to interfere in ways that alter the pulse's apparent motion. These results are not just curiosities. They provide valuable insights into the behavior of light and information. They confirm that relativity's limits apply not to appearances, but to the transmission of usable cause and effect relationships. The apparent superluminal movement of a light pulse is a kind of optical mirage, an emergent behavior of the wave's structure rather than a physical breach of nature's rules. If one tried to encode a message into the pulse, say, by switching it on and off in a controlled pattern, the earliest detectable change, the true signal, would still propagate at or below the speed of light in vacuum. Physicists have also performed similar experiments with microwave and radio waves, and even with quantum tunneling phenomena, where particles appear to jump through barriers instantaneously. In every case, the same conclusion holds. The apparent speed can exceed light's, but the transfer of information never does. Einstein's causality remains unbroken. These experiments remind us of something profound about nature. Reality often hides behind perception. The behavior of waves, especially in complex media, can easily trick our intuition. But when we examine the data carefully, when we look at the information instead of the illusion, we find that the universe remains consistent, precise, and deeply logical. And yet, even as these laboratory results affirm relativity, they also highlight how flexible the concept of speed can be. Not every motion in physics means the same thing, and not all apparent velocities correspond to physical ones. To understand this distinction more clearly, we need to look deeper at what physicists mean when they talk about apparent speed versus actual speed, and why confusing the two leads to many misconceptions about breaking the light barrier. When scientists report that light pulses or wave patterns seem to move faster than light, it's natural for the public to react with excitement and even disbelief. After all, Einstein's theory of relativity has long been understood as a kind of cosmic speed limit, one that nothing in the universe can surpass. But what these experiments truly show is not that relativity has been broken, but that the appearance of speed can be deceiving. The difference between apparent and actual speed lies at the heart of this misunderstanding, and untangling it reveals just how carefully nature guards the boundary between illusion and causality. To understand this distinction, it helps to recall that light, like all electromagnetic radiation, is a wave, a pattern of oscillations that carries both energy and information. When a pulse of light moves through a medium such as glass, gas, or fiber, it is not a single, uniform wave. Instead, it's a wave packet made up of many different frequencies that overlap and interfere with one another. The result is a shape, a pulse envelope, that represents how the energy of the wave is distributed in time and space. That envelope can stretch, compress, or distort depending on how those component frequencies interact within the medium. The apparent speed of the pulse, how fast the peak or the shape of that envelope seems to move, can vary widely depending on those interactions. In regions of normal dispersion, where the refractive index of the material changes smoothly with frequency, the pulse moves in a predictable way. But in regions of anomalous dispersion, where that relationship reverses, interference between the frequencies can cause the pulse's shape to shift dramatically. The leading edge of the pulse can be reinforced, while the trailing edge is diminished, creating the illusion that the pulse's peak has leapt forward faster than light. But here's the crucial part. This apparent motion does not mean that energy, matter, or information has actually outrun light. The actual speed, the signal velocity, or the rate at which a causal influence moves, remains safely within the light speed limit. What's happening is a kind of optical sleight of hand caused by the way the pulse reshapes itself. The wave's components interfere constructively and destructively in just the right way to make the peak appear at a new position sooner than expected, even though no part of the energy or information has traveled faster than light between those points. An analogy often used to illustrate this is that of a moving shadow or laser spot. Imagine shining a laser pointer on a distant wall and sweeping it rapidly across the surface. The spot can appear to move faster than light across the wall's surface if the distance is great enough, yet no single photon from the laser moves faster than light. The spot's apparent motion is just the geometric result of many photons hitting different parts of the wall in sequence. The speed of the spot isn't a real physical speed. It's the speed of an effect produced by the coordinated behavior of light, not by the transport of information. The same logic applies to light pulses in laboratory experiments. When the pulse appears to emerge from a medium before it should, what we're really observing is the reshaping of the wave, like a magician's sleight of hand. The part of the pulse that seems to jump ahead is already encoded in the early portions of the incoming wave. Nothing new, no new data or signal, has actually been transmitted faster than light. If you were to try to use this pulse to send a message, say by encoding a binary signal, the receiving end would still have to wait for the leading edge of the pulse, which always moves at or below the speed of light. This distinction between apparent and actual speed is more than just a technical point. It's a profound safeguard built into the structure of physics. Relativity doesn't just restrict how fast energy or matter can move. It also ensures that cause always precedes effect. If any true signal could outrun light, it would be possible to construct situations where a message arrives before it's sent, unraveling causality itself. The fact that nature allows appearances of superluminal motion, but never the real thing, is not a flaw or a coincidence. It's evidence of an underlying consistency that holds the universe together. Even in phenomena that seem utterly instantaneous, such as quantum entanglement or the expansion of space during the universe's early inflation, this distinction holds. Apparent connections can span great distances faster than light, but the transfer of usable causal information never does. In every carefully measured experiment, from the fastest light pulses to the most extreme quantum effects, Einstein's limit remains intact. So when scientists speak of faster-than-light light pulses, what they mean is that the pattern of the pulse behaves in a superluminal way. Not that the pulse itself, or any information it carries, actually exceeds light's speed. It's a reminder that the universe can be subtle, that the difference between illusion and reality is often measured not by what we see, but by what information can actually be transferred. And it's this very relationship between information, energy, and time that ties directly into a deeper principle: causality, the universal order that keeps time flowing forward. Without causality, physics itself would lose meaning. In the next segment, we'll explore why protecting causality is more than just a rule of physics. It's the very logic that underpins the universe. At the heart of the universe's most fundamental laws lies a concept so intuitive that we rarely stop to question it: causality, the principle that every effect must have a cause that comes before it in time. This simple rule, that causes precede their effects, is not just a philosophical notion. It's the backbone of physics, the invisible thread that keeps the fabric of reality coherent. Every scientific theory, every experiment, every prediction relies on the assumption that the universe operates in a causal sequence. If that order were ever violated, if effects could occur before their causes, the logical structure of the cosmos would unravel. And this is precisely why the speed of light acts as the ultimate enforcer of causality. Einstein's theory of relativity doesn't just impose a speed limit arbitrarily. It emerges naturally from the need to preserve a consistent order of events in all reference frames. In relativity, the concept of time isn't absolute. Two observers moving at different speeds can disagree on the order of events, whether one thing happened before another, depending on their relative motion. This strange flexibility of time is one of relativity's most startling predictions. Yet, within this flexible structure, there's one constant that prevents complete chaos. No information or signal can travel faster than light. Why does this matter? Because light speed defines what physicists call the light cone, a boundary in space-time that separates events that can be causally connected from those that cannot. Imagine you shine a flashlight in the dark. The expanding sphere of light defines everything your action can influence. Anything outside that sphere cannot possibly be affected by you until the light, or any signal, reaches it. Every event in the universe has its own light cone, and all possible cause and effect relationships must lie within these cones. If something could move faster than light, it would break out of this causal boundary. It could reach points in space-time that should, according to relativity, be completely inaccessible at that moment. For some observers moving relative to the event, it would even appear as if the signal traveled backward in time. In such cases, the order of cause and effect would no longer be absolute. What one observer calls the cause might be seen as the effect by another. Physics would lose the ability to define a universal order of events, and contradictions would begin to appear, such as receiving a message before it's sent, or observing an explosion before the trigger is pulled. This isn't just a philosophical problem, it's a breakdown of predictability itself. The power of physics lies in its ability to predict outcomes from initial conditions. If you know what's happening now, you can calculate what happens next. But if information could move faster than light, that predictive order collapses. An event in the future could influence the present, meaning we could no longer determine outcomes consistently. The universe would cease to be deterministic or even logically coherent. One of the most famous thought experiments illustrating this problem involves the tachyonic antitelephone, which we touched on earlier. By sending signals faster than light between two observers in motion relative to each other, it becomes possible, under the mathematics of relativity, to construct a loop where a message is received before it is sent. In such a scenario, you could send a warning to prevent an event that caused the message in the first place, creating a paradox. This kind of causal violation isn't just confusing, it's physically destructive to the concept of time itself. Einstein understood this deeply. His equations allow for many strange geometries of space-time: wormholes, closed loops, even warped regions that could theoretically permit time travel. But he believed that nature protects causality. Physicist Stephen Hawking later echoed this belief with his chronology protection conjecture, suggesting that the laws of quantum physics prevent time paradoxes by destabilizing any system that could allow them. The universe, in other words, seems to contain self-correcting mechanisms that make causal violations impossible in practice. Causality's protection is also intimately tied to energy flow. Every interaction in physics, from a ball rolling downhill to light moving through space, depends on energy moving forward through time, from higher to lower potential. This directionality defines what we perceive as the arrow of time. If causality were broken, energy could, in theory, flow backward. Entropy could decrease spontaneously, and time itself would lose its meaning. The entire thermodynamic and informational structure of the universe depends on the reliability of causal progression. Even in the quantum world, where uncertainty reigns, causality still holds firm. Quantum mechanics allows for probabilistic outcomes, but not backward influence. When two entangled particles appear to affect each other instantaneously, no information actually travels between them faster than light. The results only become meaningful when compared later within the bounds of light-speed communication. Thus, even the most mysterious behaviors of quantum mechanics ultimately preserve the chain of cause and effect. In this sense, the speed of light isn't just a speed, it's a safeguard. It's the universe's way of ensuring that history makes sense, that past and future remain distinct, and that logic remains unbroken. The light speed limit guarantees that every event has a consistent place in the web of space-time, no matter who observes it. If we ever discovered a way to circumvent this rule, it wouldn't just change how we travel or communicate, it would change the very nature of reality. Time could become fluid, paradoxes could proliferate, and the concept of before and after might dissolve entirely. The universe, as we know it, would lose its causal fabric. And yet, while causality has proven unbreakable so far, the boundaries of physics continue to evolve. At the cutting edge of research, where relativity meets quantum mechanics, scientists are probing the frontier where this cosmic speed limit might meet new and unfamiliar laws. Could there be deeper principles hiding beyond relativity's reach? Could quantum gravity, or the fabric of space-time itself, reveal new possibilities that change how we understand these limits? That's where we turn next, the current frontiers of physics, where the interplay between relativity, quantum theory, and cosmology might hold clues to the ultimate nature of information, light, and time itself. At the very edge of modern science lies an uneasy frontier, a region where Einstein's relativity and quantum mechanics overlap but refuse to fully align. This boundary marks one of the most active and profound quests in physics. The search for a theory that unites the macroscopic order of space-time with the microscopic chaos of quantum behavior. It's here, in the merging of quantum information theory, quantum field theory, and cosmology, that scientists are probing the deepest limits of the light-speed barrier, asking whether new principles might emerge beyond the reach of classical relativity. Einstein's relativity describes the universe on grand scales, galaxies, gravity, the curvature of space-time, while quantum mechanics governs the subatomic world, where uncertainty and probability reign. Both theories have been experimentally verified to extraordinary precision, yet they speak very different languages. Relativity treats space-time as smooth and continuous. Quantum physics insists that everything, even energy itself, comes in discrete packets. The two frameworks coexist beautifully in most situations, but when they collide, inside black holes or at the first instant of the Big Bang, the equations break down. Somewhere in that overlap must lie a deeper theory, and finding it could redefine our understanding of speed, information, and causality. One of the most exciting frontiers is quantum information theory, where physicists view the universe itself as a kind of information processing system. In this framework, Information, rather than matter or energy, may be the most fundamental quantity in nature. The light speed limit then becomes not merely a physical constraint, but a limit on how fast information can be exchanged across space-time. Efforts in quantum communication and quantum computing are already testing this boundary. Experiments with quantum entanglement, quantum teleportation, and satellite-based quantum encryption are revealing how information behaves under the strangest possible conditions, sometimes appearing to transcend distance, yet always respecting the deeper causal structure set by relativity. In quantum field theory, which blends quantum mechanics with special relativity, scientists have found that even empty space is not truly empty. The vacuum teems with virtual particles that constantly flicker into and out of existence. These fluctuations can momentarily bend the rules of energy conservation and light speed motion, but only for the briefest flashes of time, too short to transmit any usable signal. This quantum foam, as it's sometimes called, might be the key to understanding space-time itself as a dynamic, probabilistic entity rather than a fixed geometric stage. If space-time has a quantum structure, then the speed of light might not be perfectly constant at the smallest scales. It could fluctuate slightly depending on the energy of the particles involved. Experiments at the highest energies, such as those involving gamma-ray bursts from distant galaxies, are searching for tiny signs of this variation. But so far, the speed of light remains unwavering. Meanwhile, in cosmology, relativity and quantum effects collide on a cosmic scale. The early universe, during the period known as cosmic inflation, expanded faster than the speed of light, not by breaking relativity, but because it was space itself that expanded. This raises deep questions about how the laws of physics behave when space-time is dynamic and flexible. Some cosmologists speculate that inflation and other extreme phenomena could reveal quantum gravitational effects, subtle hints that space-time has a quantum texture that blurs the distinction between distance and duration. At the frontier of these studies is the search for a quantum theory of gravity, a framework that would unify the smooth geometry of general relativity with the discrete nature of quantum mechanics. Candidate theories like string theory and loop quantum gravity suggest that space-time might be made up of tiny, vibrating structures or quantum loops, far smaller than atoms. In these models, the light speed limit still emerges as a fundamental property, but its meaning becomes more intricate. It may arise not as an imposed rule, but as a statistical feature of how space-time behaves when viewed at large scales. What makes this research so thrilling is that it redefines what we mean by the limits of physics. The boundary between possible and forbidden isn't a rigid wall, it's a region of active discovery, where quantum and relativistic laws negotiate the structure of reality itself. Every new insight from quantum communication, black hole thermodynamics, or cosmological observation helps refine our picture of what information, energy, and time truly are. Still, despite all these efforts, no experiment has yet shown a real, physical breach of the light speed barrier. The more we learn, the more it seems that nature's limit is not a barrier to progress, but a cornerstone of consistency, a principle woven so deeply into the logic of reality that even the quantum world can't escape it. Yet in exploring the boundaries of relativity and quantum mechanics, physicists are uncovering something even stranger. Hints that the universe might have extra dimensions, hidden layers of reality where information could behave in ways we can barely imagine. And so, as our journey continues, we move from the known frontiers of physics into the speculative, but mathematically tantalizing, realm of extra dimensions, where the rules of motion and speed might look radically different from the familiar 3D universe we inhabit. Modern physics has long hinted that the universe may be far more complex than it appears, that the 3 dimensions of space we perceive might be only a small fraction of a deeper, multidimensional reality. The idea of extra dimensions isn't just a sci-fi fantasy. It arises naturally from some of the most sophisticated theories in modern science, particularly string theory and its successor frameworks. These theories suggest that the universe may contain additional spatial dimensions, possibly as many as 10 or 11, curled up so tightly that we can't directly perceive them. Within this hidden structure, information and forces might behave in ways that seem impossible from our limited three-dimensional point of view, including motion that appears to outpace light. In string theory, the basic building blocks of nature aren't point-like particles, but tiny vibrating strings. The vibration patterns of these strings give rise to all known particles and forces, including gravity. However, for the mathematics to work consistently, these strings must vibrate in more than 3 spatial dimensions. The extra dimensions are thought to be compactified, rolled up at scales smaller than subatomic particles, invisible to current experiments. Yet their influence might still subtly affect how particles interact and how space itself behaves. In this multidimensional picture, light speed, as we understand it, applies strictly to motion within our observable, three-dimensional brain, a term used to describe our universe as a membrane within higher dimensional space. But in the higher dimensional bulk surrounding it, information might follow paths that take shortcuts through these hidden dimensions. From our perspective, signals taking such routes could appear to move faster than light, when in fact they're merely traveling through an extended geometry inaccessible to us. This is sometimes compared to a wormhole-like effect in higher space. Information doesn't truly exceed the cosmic limit. It simply uses a more efficient route through dimensions we cannot see. Theories such as M-theory and various brain world cosmologies expand on this concept. They propose that gravity, and possibly other forces, can leak into or interact through these extra dimensions, which might explain why gravity is so much weaker than the other fundamental forces. Some models even suggest that gravitons, the hypothetical quantum particles of gravity, could travel through higher dimensions at speeds that would appear superluminal to observers confined to three-dimensional space. In this sense, faster-than-light motion might not be a violation of physics, but a reflection of our limited dimensional perspective. To visualize this, imagine an ant walking along a flat sheet of paper representing our three-dimensional universe. If the paper folds, the ant must crawl along the curved surface to reach another point, following a path constrained to its two-dimensional world. But a being capable of stepping through the third dimension could move directly between the 2 points, bypassing the long route on the paper. To the ant, it would appear that the higher dimensional traveler had moved instantaneously, faster than light. From the higher dimensional viewpoint, though, no laws were broken. The motion was simply more efficient because it used geometry inaccessible to the ant. This kind of speculation leads to fascinating possibilities. If extra dimensions exist and can be accessed or influenced, they could, in theory, allow for shortcuts in information transfer or even travel, similar in spirit to wormholes but rooted in higher dimensional geometry. In fact, some models of string theory predict the existence of Kaluza-Klein modes, particles that move through extra dimensions and might interact weakly with our own, potentially revealing evidence of these hidden spaces. Detecting such effects, perhaps through deviations in gravitational strength at microscopic scales or through high-energy collisions at particle accelerators, remains one of the goals of experimental physics. However, it's important to emphasize that so far, these ideas remain purely theoretical. No direct evidence of extra dimensions has been found, and attempts to detect them have yet to yield measurable results. But their mathematical consistency and explanatory power keep them at the forefront of theoretical physics. They offer elegant frameworks for unifying all forces and particles, including gravity, under one set of laws. If extra dimensions do exist, they could fundamentally reshape our understanding of what speed means. A signal that seems instantaneous in 3 dimensions might simply be taking advantage of higher dimensional geometry. From that vantage point, the speed of light remains inviolate, but its role as the cosmic limit could take on a richer, more layered meaning. These ideas hint that our universe might be only a shadow of a grander, multi-dimensional reality, and they bring us closer to an even deeper realization that the meaning of motion and speed depends profoundly on how space-time itself is structured. Indeed, as we'll explore next, even within our known universe, the concept of speed becomes flexible when space-time itself expands or curves, as seen in the vast, accelerating cosmos around us. When we talk about speed, we tend to imagine it as something simple: the rate at which one object moves relative to another, measured in kilometers per second or miles per hour. In everyday life, speed feels absolute. If a car travels 100 kilometers per hour, it's going 100 kilometers per hour no matter where or when. But in the deeper fabric of the universe, speed is not a single, universal concept. It's relative, it's local, and in the context of curved space-time, it becomes something far more subtle than just distance divided by time. Einstein's theory of general relativity showed that space and time are not static backdrops. They're dynamic, malleable, and responsive to the presence of mass and energy. When space-time curves, what we perceive as motion can be an effect not just of objects moving through space, but of space itself stretching, bending, or flowing. In such a universe, speed depends entirely on the frame of reference, on what you define as stationary and what you define as moving. This becomes crucial when we look at the largest scales of all, the expanding cosmos. During the first fractions of a second after the Big Bang, the universe underwent an extraordinary phase known as cosmic inflation. In this brief moment, lasting only about 10 to the negative 32 seconds, space itself expanded exponentially, doubling in size over and over again at an incredible rate. Regions of the universe that were once microscopic became separated by vast cosmic distances. During this process, galaxies, or rather the primordial matter that would form them, were carried apart by the expansion of space-time so quickly that their separation increased faster than the speed of light. At first glance, that sounds impossible, a direct violation of Einstein's cosmic speed limit. But here's the key distinction: nothing was moving through space faster than light. Instead, space itself was expanding. The galaxies were not racing through the void at superluminal speeds. They were stationary with respect to their local regions of space-time, while the space between them stretched. Relativity's light speed limit applies only to motion within space-time, not to the expansion or curvature of space-time itself. Even today, billions of years after inflation, the universe continues to expand, though much more slowly. As a result, distant galaxies are receding from us, and the farther away they are, the faster they appear to move. Beyond a certain distance, about 16 billion light-years away, the expansion of space carries galaxies away from us faster than light can travel. This doesn't mean those galaxies are breaking relativity. It simply means that the space between us and them is growing faster than light can bridge the gap. Light emitted from those galaxies today will never reach us, because the universe expands faster than the photons can traverse the widening gulf. This phenomenon reveals just how flexible the concept of speed becomes in curved space-time. Locally, say, between a planet and its star, the speed of light remains absolute and unbeatable. But on cosmic scales, the geometry of the universe itself changes the rules. What we think of as motion may, in fact, be the manifestation of space-time's own dynamics. In this sense, it's not that anything is traveling faster than light, but that the metric that defines distance and time is itself evolving. Another powerful example comes from regions of intense gravity, such as near a black hole. To a distant observer, an object falling toward a black hole appears to slow down and never quite cross the event horizon, the point of no return, because light from the object takes longer and longer to escape. But to the falling object itself, time flows normally, and it crosses the event horizon in finite time. Each observer's experience of speed and time is valid within their own reference frame, yet completely different when compared across frames. This illustrates that in curved space-time, motion and causality are inherently local phenomena. You can only meaningfully talk about speed in relation to what's happening in your immediate region of space-time. Physicists often describe this by saying that relativity preserves local causality. No object or signal can exceed the speed of light relative to its nearby environment, no matter how warped space-time becomes. But globally, over large distances or in rapidly changing geometries, the separation between 2 points in space-time can increase faster than light without any law being violated. The universe allows for expansion, warping, and curvature that can mimic superluminal effects, yet all remain consistent with the structure of relativity. This subtlety has profound implications for how we think about communication, distance, and even isolation on cosmic scales. There are regions of the universe so far away that no signal we send, no matter how long we wait, will ever reach them. Likewise, light from those regions will never reach us. The universe is divided into causally connected regions, separated not by walls or barriers, but by the relentless expansion of space-time itself. Thus, in curved space-time, speed becomes less about how fast something moves and more about how the universe itself changes beneath it. A photon racing through interstellar space always travels at light speed locally, yet cosmic expansion can stretch the very path it travels, dilating time and distance in ways that make it seem slower, or in other contexts, faster. Understanding this redefinition of speed leads us back to a deeper truth. The cosmic speed limit isn't just a number, it's a principle that ensures consistency amid the universe's ever-changing geometry. It preserves local order even as space, time, and motion dance on cosmic scales far beyond human intuition. And this brings us to a final, more philosophical reflection. If speed, distance, and even time itself are relative and flexible, what does it mean for information, or for us, to have a limit? Is the light speed barrier a constraint on our imagination, or is it a window into the deeper logic of existence itself? When we reach the end of the scientific trail, the equations, the measurements, the boundaries, we inevitably find ourselves staring at a deeper, more philosophical horizon. The question of whether information can travel faster than light isn't just a question about physics anymore. It's a question about what kind of universe we live in, and perhaps even what kind of beings we are within it. What does it mean that there is a speed limit, not just for motion, but for information, the very currency of cause and effect? Does this limit represent a cosmic constraint, a barrier to what we can achieve? Or does it reveal a deeper truth about the logical structure that makes reality coherent in the first place? Every act of discovery in physics begins as an act of imagination. We dream of bending time, folding space, sending messages across the stars. The light speed barrier seems, at first glance, to mock that ambition, to tell us that no matter how far we reach, there will always be delays, always distances too vast to bridge. It's humbling, even disheartening, to think that the fastest thing in existence, light itself, still takes over 4 years just to reach the nearest star. Yet within that humbling truth lies something profound. The universe is consistent, even if it is not infinitely permissive. The light speed limit gives the universe order. Without it, reality would dissolve into paradox. Causes could happen after their effects, signals could arrive before they're sent, and time itself could lose meaning. The finite speed of information ensures that the world unfolds in a way that can be understood, predicted, and experienced. It means that the cosmos has a logic, a rhythm that binds together every atom, every star, and every thought. This limit is not a cage. It's a framework, a kind of scaffolding that allows meaning and memory to exist. From a philosophical standpoint, it's fascinating to realize that ignorance and delay, the time it takes for information to reach us, are not flaws in the design of reality, but integral parts of it. The fact that we see the universe as it was in the past, not as it is now, connects us to the grand flow of time. We are always observers looking backward, witnesses to an unfolding cosmic narrative. Light's finite speed turns the universe into a living history book, one where every star and galaxy tells a story billions of years old. If information could travel instantaneously, that story would vanish. Everything would collapse into a single, timeless moment. The delay gives reality its texture. There's also a certain beauty in the way this limit challenges human curiosity. It forces us to think creatively, to find ways around, not through, nature's constraints. Instead of despairing over the speed of light, we learned to use it, to measure distances, to understand the universe's age, to communicate with spacecraft millions of kilometers away. The very technologies that define modern civilization, lasers, fiber optics, GPS, all rely on our mastery of light, not our defiance of it. In that sense, the light speed limit has become not a boundary to fear, but a guidepost that helps us map the possible. It's also worth considering that a limit, in philosophy, is often what gives meaning to potential. A boundless universe, without constraints, would be a place where nothing stands out, nothing matters. Limits define shape, structure, and purpose. The speed of light is one such limit, a cosmic rule that ensures the universe has a rhythm we can understand, a structure we can exist within. Far from constraining imagination, it inspires it. Our longing to reach beyond that limit, our constant search for loopholes through warp drives, wormholes, or quantum entanglement, has driven some of the most profound insights in science. Perhaps the real question isn't whether we can go faster than light, but why we want to. The desire to outrun light is, at its core, a desire to transcend separation, to conquer distance, time, and isolation. It's a reflection of humanity's endless yearning for connection and understanding. And yet, within the constraints of physics, we find a mirror of ourselves, a species bounded by the laws of nature, but forever reaching to understand them more deeply. Seen this way, the speed of light isn't an obstacle, it's a language. It tells us that information, causality, and existence itself are woven together in a single, harmonious pattern. The fact that we can even conceive of this limit, measure it, and question it is evidence of our participation in that pattern. We're not separate from the laws of nature, we're expressions of them. So when we ask, can we send signals faster than light? We're really asking something much larger. Can we transcend the structure of the universe itself? And perhaps the answer, paradoxically, is that understanding the structure is the only true transcendence there is. In the end, the light speed limit reminds us that our quest for knowledge is not about breaking nature's rules. It's about discovering why those rules exist and what they say about the unity of everything. The barrier of light doesn't confine our imagination, it gives it direction. It points us not toward defiance, but toward deeper understanding, toward a universe that, though finite in speed, is infinite in wonder. And that brings us full circle. The realization that the light speed barrier isn't the universe's way of saying no. It's its way of saying, this is how reality holds together. It invites us to explore, not to surpass the limit, but to understand why it's there. In the end, the light-speed barrier is not a wall to be shattered, but a thread that holds the cosmos together. It preserves causality, ensures order, and gives time its direction. Without it, reality would unravel into chaos. The dream of faster-than-light travel may forever remain out of reach, but that doesn't diminish our pursuit. It enriches it. For the true frontier isn't about breaking nature's limits, but about understanding them, why they exist, how they shape reality, and what they reveal about our place within it. The speed of light isn't the universe's way of confining us. It's its way of keeping the story coherent, a cosmic reminder that every boundary we encounter is also an invitation to deeper insight. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.